a step ahead. Yeah, just step here.
Oh, this is perfect. This spot's perfect. Okay. All right, guys. Now that we're set up, today we're going to be tackling the problem of a finite line of charge, of uniform charge distribution, and the electric field that that creates. So we'll draw our line here of it's not a straight line. We'll draw our line here of electric charge. It has a uniform linear charge density lambda, and we're going to be talking about some arbitrary point p, some distance away. Now, it's important for this specific problem that p is exactly at the midpoint of this line. We'll talk about why that is in a little bit. So what we're going to start by doing is considering some infinitesimal charge segment here that we're going to call dq, some point in the line. And dq is going to be distance r from the point. So that's a straight line. Now, r obviously has an x component and a y component, so it'll have it'll be x away, and then this way it'll be y away, and it'll create a right angle triangle here. So we can use Pythagoras theorem, of course. Now we will also say that below this distance here for the bottom half is a, and then likewise the top half is a as well. So the total length of the bar is 2a. Okay, good. Now, one thing that's useful to keep in mind is the fact that if we consider some equal and opposite charge, as there is here, because we talked about how it's exactly in the middle on the up-down axis, that the y component that we talked about here, the y, if there's some other dq down here, which there is, would cancel out. So the y component actually vanishes in this, so we're only concerned with the x component. Likewise, we can set out a few equations here. So we know that, by definition, the density, linear charge density, is equal to the charge over the length. And we know that the length is equal to 2a, so we can say the density is equal to q over 2a. And then, since we're talking about infinitesimals here, we can do, because we're going to be doing calculus in a little bit, we can talk about this specific dq up here, and how dq is equal to the density, lambda here, times dy. Because dy is like this distance here that dq inhabits. So if we rearrange this, we'd have lambda equals dq over dy, just like we have lambda equals q over L, which is just sort of in the same axis as y. We also remember that the electric field in general, E, is just equal to K, which is Coulomb's constant, Q over R squared, which is this R here. And then if we find the infinitesimal version of that, dE equals K dq over r squared. Now, since we talked about how we're actually only concerned with the charge in the x component, and this is the r here, to find on any right triangle like this, if this is a right angle, then our x here is actually, if this is r, our x is just r cos theta, and our y, if we drew it, would be r sine theta, but like I said, the y components are going to cancel and be 0. Now, also, because of the way cosine works, we know that that's just equal to the adjacent over the hypotenuse, and we're talking about this angle here. So in this case, it is indeed just x over r, which you could see by rearranging this equation anyway. So, since we're only concerned with the x component, we end up with dE sub x, because we're only concerned with that, is equal to dE x over r. Likewise, it would be y over r for the y component, but again, we're not concerned with that right now. So we have dE of x. If we substitute in this dE up here, we get k dq over r squared, x over r. Sorry, I should be using a capital R to be consistent. And then we know from up here, we know that dq equals lambda dy, and lambda is q over 2a. So plugging in the lambda here, we would have dq equals q over 2a dy, and then plugging in the dq down here, we get dex equals k kqx over 2a r squared r, which will just be r cubed in the next step, and then dy. That's the important bit. So now I'm going to just make a new page because we're out of room here, but we're just going to simply integrate this dx here. So dEx equals just writing what we had last page here, kqx over 2a r cubed dy, and then we're just going to integrate both sides. The integral of dex is just ex. And then we're actually concerned because our bar goes between negative a and a, because our bar goes between negative and a, and we're concerned with the charge of the whole bar. We're going to integrate between, as you guessed, negative a and a of kqx over 2a. And then what is r? R is actually x squared plus y squared, right? The square root of that, by Pythagoras' theorem, since we talked about it, well, we talked about it on the last page, but then it's cubed. So this ends up actually being to the power of 3/2, because we're cubing a square root. I won't be spending any time integrating this integral because I'm in the forest, but you can integrate it on your own or use Wolfram Alpha or something to find out that this integral evaluates to kq over 2a, which are constants, so we just took those out front, times y over the square root, or sorry, x times the square root of x squared plus y squared between negative a and a. Now, if you know anything about evaluating square roots, or sorry, evaluating definite integrals, we're just going to do that with the a terms here and end up with ex equals kq over 2a. Then plugging in our a's here, a over square root of x. There's an x out front, my bad. X squared plus a squared, and then minus a. So that'll end up being a plus a, x over x squared plus y squared, square rooted. And then because we have minus minus and the denominator is the same, we end up with kq over 2a times a over x square root x squared plus y squared. And then this a, because we're doing minus a negative, ends up being 2 because we're just adding it. And then we can, as the very end here, just sort of a cleanup step, we will notice that the two a's can actually just cancel with each other, and we get kq over x, the square root of x squared plus y squared. Small amendment, sorry, this should be a squared down here. That's my mistake. This one should be a squared. And this is indeed the electric field in the x direction for a finite linear charge of constant charge density. Exercise to you, the viewer, go through the same process I did for the y component of the electric field, and you'll find that it is 0, as I said at the beginning. From that sort of intuitive explanation, you should be able to prove that mathematically pretty easily with the same process. Another fun exercise is what if the line of charge extends infinitely in both directions? It actually cleans up this expression a little bit. The expression is a little bit cleaner in the case of an infinite charge length, but I'll leave that up to you. I think I hear some coyotes, so I'm gonna head out. Thanks for coming to my forest lesson, and I hope this was informative.